So hi guys, back to another episode of Building Tensorflow. Alright, so last time we we built our computational graph and we actually did a backward prop and we got the right answer. Today we will add another operation, let's call it an add operation, and then we will structure this whole thing into multiple files because this is getting too long. So our comfort level. So anyway, so let's try to modularize this a bit. Let's say operation. Let's make a general class called operation, and then we will extend from that. Let's see. So operation. Operation, what does operation generally have? Let's check this out. You know, this has two things, so let's copy this and generally we have a backward and a compute. So right now we are assuming that every data that flows through this graph will be a flow tensor, so we're not making this generalized. We're moving forward with flow tensor. Then if the time comes, then we will introduce like int, double, or different data types. Anyway, so generally we have backward and compute in this. So now when we want to extend this function, so extend this class, what we do is we inherit it. So inheritance happens like this. You specify the access modifier. So let's say everything is public, so everything is visible to multiply operation when it tries to look into operation. So we have that, and also we want to create kind of an abstract class where we tell the compiler that when you actually run backward on multiply operation, you should run the definition specified in multiply operation and not in operation. So to do that, there's something called virtual functions in C++, and we do this like this, and then so we leave it at that, and then we actually extend it. So now when the main program calls backward operation dot backward, it will actually see what kind of operation it is and then call backward according to what operation it is. So for a multiply, it will switch the gradients, and for an addition, it will distribute the gradients. So anyway, so we have multiply operation here, and let's make another add operation here. Add operation here, and it's similar, it's the exact same thing. We just specify we have two operands, we have backward and we have a compute. Alright, so this is quite simple. Now we'll have to change flow tensor to accept a generalized version of operations. So that's the benefit here. We don't flow tensor doesn't need to know what kind of operation it's going to go forward with. Right, that makes sense, right? So as you can see, this line will work because multiply operation is inherited from operation, so this won't error out. So let's make like an addition thingy. Alright, add operation, and let's say this is a plus, right? That's quite simple. Now we'll just code the backward propagation for an addition, and operation, and so this will be a plus, right? And this will be just in addition, you just distribute the gradient that is coming in backwards. It's very simple. So this is the distributing case. So as is, right? All right. So we've done this. Now let's see if it runs or not, right? So let's say we have something called 4, right? 4, and let's say this is 10, right? And then let's say flow tensor 5 equal to 3 plus 40, and let's 5 rod backward. And then forgot this. This is something we solved in like the lecture before this one. Right, this should work. We'll try to solve this part. I don't the and looks really ugly here and it's counterintuitive, so we'll solve that in some later lecture, but let's focus on this for now, like, because we have a lot to get to. We have to actually modularize this thing and convert it into header files and stuff. So yeah, this is backwards. So what should our gradient be? 5's gradient is 1, as we know. Let's say what's 4's grad? Let's say 3 grad and 2 grad. We already have 1 grad. 1 grad. So let's think this out. What should the answer be? For 4, it should be 1 because it's just added, right? And similarly for 3, it should be 1. And for 2 and 1, it should be 1, 1, 2, 2. So that should be the printout. Let's just compile this thing. Right? Looks good, I'd say. Okay. So this is main. Okay, undefined reference for vtable for operation. So this is an error I actually encountered when I was testing this out, and this is because this is not defined as such. And when we've created multiply operation and add operation, we've just defined it. The main thing is that, like, this is not a pure virtual function, and you need to have a pure virtual function to make it like totally abstract class, an abstract class in C++. So like this small change will solve this error. I know it's one of those things that is one of C++ peculiarities and make it really tough for newcomer to get into. I'll go into detail into more troubles that I'm facing trying to modularize it, but for now let's just run it, right? 1124, that is what we wanted. Yep, this is right. 2's value goes into 1 and 1's value goes into 2. That's right. So let's try to split it into header files, right? Okay. So this is really interesting. So let's create like an operation dot header file, right? Let's just paste this part into header files. Okay. Now pretty simple, right? Now let's try to just get these two. Let's get multiply operation in a separate file and add operation in a separate file. So add operation dot h, and let's say multiply operation dot h. Okay, so multiply operation is here, but we first need to include our operation.h because it does not know anything. about what flow tensors are. So that solved the error, and let's copy this. Similarly, an add operation. So let's just copy add operation to this. Yep, that sounds good, right? We've copied it. Let's create, similarly for float tensor, let's create another class. Alright. So header files are just meant for defining our classes and objects and whatever and functions, and we actually declare them in other C++ files. And you take all these 4 or 5 C++ files, one for add operation, one for multiply operation, one for flow tensor, and then link them together using GCC, and then you finally get the final output, and then you run your entire thing. So that way your project is scalable, right? You won't have amazingly big files, and you can run individual components separately because they'll have separate C++ files. But yeah, that's the one problem I'm facing right now. We won't be able to do that, but let's see what we were able to do until now. We were at flow tensor, right? Flow tensor.h. Okay, what does flow tensor need? It needs obviously operation. So that's done, and it needs multiply operation and add operation. Okay, then let's add it. Okay, what is happening? C++ code is pretty good. It is really smart type suggestions, and I wasn't expecting like a small, like simple text editor. This is not an IDE, right? So to do all this, but it does pretty well. It's got IntelliSense. It's pretty cool. So we've added this, and this works, right? So now what we do is let's just remove all of this, right? And let's just include. What do we want to include? We just want to, let's say, build Tensorflow. And let's create another header file. Build Tensorflow.h. And then what we'll do is we'll just call flow tensor, I guess. Nothing much to do. Flow tensor, right? Because essentially that's the one thing we're using in a main file. So it's great to abstract our logic into different parts, so the end user has no clue like what kind of classes and what our class structure is and stuff like that. So we just have flow tensor here, and it makes sense to just go build TensorFlow. So yeah. So sorry for that. So this should run, right? Okay, so let's try it out. Let's just think. So what we've done is we've abstracted everything into this build TensorFlow header file, and we go into build TensorFlow, we get into flow tensor. Okay, so flow tensor, actually build TensorFlow is like, we don't even need it right now. We probably need it afterwards for abstraction. This is just confusing. Let's just call it flow tensor. Right. Anyway, so we can actually abstract this part out into float tensor, right? Right, we can do that. So now it's much cleaner, right? Float tensor, and does this run? Nope. So we've got all these errors of redefinition. This generally happens when, I'll show you an example. So you go into float tensor, you go into operation.h, right? And then you just, so header files just copy or includes like include statements just copy the header file. So when you're here, this is replaced by the code here, and then when you go into add operation, right, so you're calling operation.h again. So when you come back here, you actually copy the code of operation.h twice. And similarly for multiply operation, we have this header file. So we're actually writing the same code thrice. And unlike Python or Java, C++ does not offer like automatic safety against this. So we need to handle this. So the way we handle multiple includes of the same header file in C++ is through something called like an if-def and an if-and-def thing. So it's really good practice to just include like header guards. They're called header guards. So what header guards are? They'll just they'll see if the header file has been called from somewhere. If it has, then it will just skip this block of code, and if it hasn't, then it will paste it. So let's see how this is done. You go, let me just see, I've forgotten the syntax of this. Yep, so that's your code. If and def whatever, and define. So if it's not defined, define it, or else like end if. So if and def, if this is defined, you skip till here, and if it's defined, and like if it's not defined, then you go here. All right, let's just copy this code. Right, operation, and you just use end if. All right, and we'll use this in our we'll use this in all our header files. Okay. Header guard is so important. If it's included, let's see if multiply. Multiply included. Let's add this to add operation 2. Add. And let's add it to float tensor. Let's name it tensor and float. And then finally have like NF here. Let's go back here. See if this runs now. It runs, and main, if I do main, we arrive at the same exact answer. Alright, that's all for today. But so I'm going to tell you for a bit of the problem I'm facing right now. So what I actually want to do is create separate C++ files for multiply operation and add operation, so that we can remove this ugly code that's not related to float tensor. It's actually related to operations, and put it to like in different C++ classes. So something like so multiply operation will just get multiply operation and float tensor, and then you just define it, and then finally like I actually with this code I actually create the binaries of the separate add operation, multiply operation, and then I actually link these binaries together with the main CPP, and then finally run this. So that'll make it really scalable, and this float tensor file won't grow out of reach. So I'll try to get this sorted, and if I do, I guess that's what we're doing in the next lecture. So anyway, just a quick reminder of our game plan right now. Our game plan is going along smoothly. So we're using float tensor for everything now. Then in the next lecture we'll create sigmoid operations. So that's the back propagation for a divide, one by something, and the back propagation for the exponential function, and we'll actually check if our backward propagation works well, and then I think we'll write tests for that. So tests for if the computational graph is working as needed, so that we can start building those test cases, really make great code out of this. And then we will actually discover in the next few lectures, then we'll create an array tensor class, so that we can and then check our backward propagation and forward propagation with arrays. And then we'll use matrices using this array tensor class, and then finally code our stochastic gradient descent optimizer, then finally train a MNIST hopefully. So that's the plan, and if possible we'll put the matrix multiplications on the GPU. So that's the rough plan right now, and I hope we stick with it, and hopefully you and I will both learn a lot about how C++ works, how it's structured, and also about computational graphs, because they're awesome. Okay, thank you so much. See you next time. Bye bye.